Ever wonder how an AI can actually follow a long story or translate a really complex sentence? The magic isn't just about processing words, it's about remembering them. So today, we're going to pull back the curtain and demystify the memory of modern AI. We're diving deep into a special kind of neural network, the long short-term memory network, or as you'll hear it called, the LSTM. Okay, let's think about this for a second. Take two sentences. First one, the apple is red. Super simple, right? Now how about this one? The apple, which fell from a tree in a sunlit orchard yesterday, is red. Now for us, it's easy. We know the main point is that the apple is red. But for an AI, all those extra words in the middle, they can make it completely forget what the sentence was even about in the first place. And that's the whole challenge. How do you connect words that are really far apart?
And yeah, this challenge has a fancy technical name, the vanishing gradient problem. But honestly, a much easier way to think about it is like a game of telephone. With basic neural networks, the message just gets weaker and more distorted the further it has to travel. So by the time you get to the end of a long sentence, that critical piece of information from the beginning, like the word apple, has pretty much faded to nothing. These networks, for all their power, basically have terrible short-term memories.
So how do we fix this memory problem? Well, you build a better brain, a neural network that's designed to remember things for the long haul. So let's meet the fundamental building block of this whole solution, the LSTM cell. So the real genius behind the LSTM is that it creates two separate memory lanes. You've got the hidden state, which is kind of like your own short-term memory. It's what you're thinking about right this second. But then you have the cell state, and this is the absolute game changer. Think of it like a conveyor belt of information, specifically designed to carry that crucial context, like our apple, safely across these really long sequences without it getting lost. But how does the LSTM decide what information gets to ride on this special conveyor belt? I mean, it can't be a free-for-all, right? It's not. The flow of information is super carefully controlled by three intelligent mechanisms that we call gates.
First up is the forget gate, and its job is pretty much exactly what it sounds like. It looks at the old long-term memory, it looks at the new information coming in, and it decides what's just not relevant anymore. It gives a score somewhere between 0 and 1 to each piece of old information. A 0 means, yeah, forget this completely, and a 1 means, definitely, 100% keep this. It's basically the cell's cleanup crew.
Okay, next, the LSTM has to figure out what new information is worth remembering. And this is a two-part thing. First, the network comes up with some candidate information, potential new stuff worth keeping. Then, the update gate acts like a bouncer, deciding exactly how much of this new info actually gets to be written into the long-term memory.
And finally, we've got the output gate. So, the cell has just updated its long-term memory, right? It's filtered out the old junk and added in the new important stuff. This gate's job is to decide what part of this now pristine long-term memory is actually going to be used for the immediate next step. It creates the output and sets up the short-term memory for the very next moment in time.
So, we've talked about the what. Now let's get our hands dirty and see the how. We're going to walk through a single calculation, step by step, to actually see these gates in action and watch how memory gets updated.
All right, to really see how this works, we need to kind of freeze time. Let's just pause the whole network at one specific moment. And at this instant, it's juggling three things: a new piece of input, its short-term memory from the last step, and of course, its long-term memory from that same last step.
Here are our starting ingredients, and they're represented as these lists of numbers that we call vectors. Just think of these vectors as how the AI represents ideas and context in a way that math can understand. So we've got a vector for the previous short-term memory, one for the current input, and one for our all-important long-term memory. Let's see what the cell does with them. Okay, let's kick off the calculation. The very first thing this cell does is decide what to forget. It grabs that previous short-term memory and the current input, and it feeds them both right into the forget gate.
So how does the gate make up its mind? Well, it takes our inputs, multiplies them by some numbers it's learned are important, we call those weights, and then it adds another learned number called a bias. This chart is just showing a part of that process. The main thing to get here is that it's a simple, structured calculation that combines the past and the present to make a really smart decision.
And after one last little step, here it is, the forget gate's final decision, in vector form. And these numbers, they are the critical part. They're telling the cell to keep about 64% of the first piece of old memory and about 43% of the second piece. You see, it's not just a simple forget or keep, it's a really precise, nuanced choice. Now, let's see how that choice gets used.
Okay, now we get to the main event. The forget decision has been made, and let's assume we've also calculated what our other gates want to do. We can finally update that long-term memory, the cell state.
All right, we have all the ingredients prepped and ready for the final step. We've got our forget gates decision, the original long-term memory, and we've also calculated our update gate, which, remember, decides what new information to add. Now it's time to put it all together.
The update itself happens in two main parts. First, we multiply the old memory by our forget vector. You can see how that scales down the old information, right? Second, we multiply the new candidate memory by our update vector to decide how much new stuff we're going to add. And then we just add those two results together. That's it. And there it is, the result of all that work. This is our brand new long-term memory. This vector now holds this perfectly curated blend of information. It's tossed out some of the old, irrelevant stuff and mixed in just the right amount of the new, important stuff. This is the memory it's going to carry forward.
And that, right there, is the whole magic trick. The long-term memory doesn't just get wiped clean at every single step. No, it is meticulously, surgically edited. And this ability to make these small, precise updates is exactly what lets important context survive that long journey across a sentence.
So let's zoom back out for a second. We've been down in the weeds with the nitty-gritty calculation. Now let's connect it all back to the big picture. Why does this whole complicated system of gates actually make for better memory? So after all those calculations, here's where our little LSTM cell lands. We've got our new, updated long-term memory, and using that output gate, we've also produced a brand new short-term memory that gets passed right along to the very next step. The cycle is now complete. So here's the advantage in a nutshell. That cell state we've been talking about, that conveyor belt, think of it like a protected information superhighway. And the gates? They're the intelligent on-ramps and off-ramps, carefully controlling the flow of traffic. This whole structure allows critical information to travel for miles and miles down that highway without getting corrupted or lost in some traffic jam. And that directly solves that short memory problem we started with.
You know, ultimately, it all comes down to this one single powerful idea. This entire elaborate architecture of gates and states, it's all built for one purpose, to preserve important information over time. Period.
So we've just seen the incredibly detailed decision-making happening inside just one single cell. And that leaves us with a final, massive question. What happens when you connect billions of these tiny memory keepers together, all learning and remembering at the same time in concert? Well, that's not just a better memory, that's the foundation for the kind of complex intelligence we see in the AI all around us today.